So essentially, kind of an overview if some of you weren't there last week. We are in the part 1 of this series. We are trying to go over some of the basics and some of the AI libraries and tools that we usually use to build AI workflows. We are looking at some other people's work and how they have formulated problems and understanding the code, understanding setting the stuff up. Last week we gave some introduction to some of the basics, like what an tensor is, what dimensions are, how we would manipulate dimensions to fit to a certain kind of an input-output to a system. And then we built a very basic multi-layer perceptron network. We're going to build on that this week. Going to talk some more about PyTorch and how to set up problem statements. And then we're going to look into convolution neural networks, which is more of a popular one when solving image processing problems. And then we'll work our way into Keras and see how Keras is slightly different from PyTorch. But I generally feel that all of these AI libraries now have a wrapper, one way or the other, that does the same thing. And once you understand the models and how they are built, you can use any tool to do it. But then a lot of other people have very strong opinions around this. So last week, this is, if you have the repo, this is the PyTorch basics. We kind of looked at installing Torch and the setup, and then how you declare different kinds of arrays. 2 and 3 are dimensions, where 3 is the number of columns and 2 is the number of rows. Or you can also say that 2 is like one list is an entity of features, where each of these columns is a dimension in that feature. So if my pixel on my screen was a list, and this was one pixel, then this would be my red, blue, and green pixel strengths that represent the color of that pixel. And then this would be another pixel. And then if I had 1024 pixels, then that's what I would end up being my screen. So this would be the representation of an image when I have the data, and then I would need to change this representation such that I can feed it into a network. We can think of neural networks not learning per image or per input. It usually learns in batches, and then it runs over an entire data set in multiple batches and over many epochs, which is how many number of times you process the whole data set, which is already split up into, say, 32 batches. So there are different ways of doing this manipulation of your input data. We can do something like view, which changes the dimensions. If you have a 10-5 array declaration or a tensor declaration, and you say, I now want 10 columns, and figure out how many rows that needs to be generated, then that's a -1. And then you can also transpose or sort of flip your image, flip your screen, that sort of thing. And then one very crucial thing in training neural networks is squeezing and squeezing, which is how many, like how the input layer of a network is set up. You want to like set up your input data in that fashion that it can take in the data. Most of the errors that you will face will be around dimensions and if you haven't processed your data correctly. So something like this array, if your input took one whole array, then this would be the representation, and this is one array representation, and there could be multiple such arrays in your input data, which you were feeding. But then you could also say 1, 2, 3, 4 are the actual inputs themselves. So something like in this slide, you can say that age was not a single scalar value. Age was a list of values and had its own distribution, and in that case it's a list. But age then can be a scalar value, which is then 1, and then income is 2, and employment is 3. So then you have to separate out each of these dimensions of your input into separate entities and feed that into a network. So manipulating your data input output is a very big part of designing systems. So at this point, you might want to set up TensorFlow. TensorFlow is now the internal of Keras, and so to use Keras, you first install TensorFlow, and we can access the Keras wrapper from TensorFlow. Keras doesn't have a separate installation of its own. And then these are the documentations that's most relevant. And also, if you don't know what Colab is, you can definitely check it out. It's all of these libraries and documentations are now active notebooks that people can actively run through, which is different from like usual coding tutorials that you find on Stack Overflow. AI kind of this whole area of development has set up these collabs where sometimes looking at the solution and Stack Overflow is just not enough. So you can run through many of these recipes, it's called, that they have already set up for you to understand how their workflow should be. Now, we also looked at a basic model. We are still using some of the prepackaged data that comes with Torch and Keras. MNIST is a very popular data set, which is numbers from 0 to 9. And you have to detect these numbers or classify if a number is 0 or 1 or 3 from the input image. So this is what an input image looks like. To load this data, you first use a dataset MNIST class in Torch Vision, and then you process that into a data loader, and usually Torch will use its inputs in form of a data loader. So you convert this dataset object into a data loader object, and then you can recurse through it. Either you can serialize it into a list, or you can loop through it, or we'll look at some other techniques of accessing this data today. And now, when you have this data, you might have different kind of dimensions, depending on how each of these libraries have packaged it. So it's always good to check for the size of a data, which will give you how many rows and columns. It's also good to check the type. It could be a list, it could be a torch tensor, it can be an array. So, depending on what you're processing the data for. So if you wanted to process it in NumPy, you need to first convert a torch to a NumPy array. Or if you wanted to train a model, you want to first convert an NumPy array to a torch. So checking the data type and the data size is important, because if you're then trying to plot this image, you need something, a 28 by 28 matrix, which is like a 2D two-dimensional array, and each of these points in that matrix has a value. That is what this IM show will plot. And so then if your data size was dimension was in a batch or something, then you need to split it out and you need to see it in this scale so that you can debug things or plot things. So these are also other different techniques of looking at the data and processing it. Now we build a very simple network. We built linear layers, which are something like this. A linear layer, we told it the input dimensions of our image. And in this case, we are feeding that image not as a matrix, but as a list. So we take the first row of that matrix, then we append the second row to that first row, third row, then to the first and second row, and we unfold that matrix into one big array. And we say if my image was a 28 by 28 image, now it's a 28 cross 28 list. And then so that is my input to my first layer, and that's the number of neurons that we want in our hidden layer. And then from this, however number of hidden layer is in the first one, the second layer needs to have input same as this one. So here, if this was 3, then 3 weights are going to 4 neurons in the second layer. So we can have this as something different. We can say this to be 1 and this as same as before. And then we can say this is neuron 2, and we can say this to be neuron 2. So as long as this input is same as the previous output, we are good. Then the connections of weights will be formed correctly. Then we also spoke about what activation is. So in each neuron, you are feeding in the input data. It has a weight associated with it when it goes to the next neuron, and then to activate that neuron, to actually process this input data as an X independent variable and that make this neuron a function of this X, you need to define that function. So that function is what this activation is. ReLU is a conventional activation function that is used. And then you have a final layer function would be depending on your problem statement. Here we used softmax because we have 2 classes. Here we had 10 classes, 0 to 9 digits, and we want a probability that given an input, how likely it is that this is either a 0 or a 9 or a 5. So each of them had this continuous value, a 0 to 1, kind of a probability of something being this class. And then once you have that probability, you take an argmax or whichever probability was the highest, that class you take as the output. So this is sort of like the basic construction of a problem. We're going to look at some more constructions. And then how to train a model is that once we have set up this network architecture, we make an object of this network, and then we can pass this data either by calling the forward function of this object, or we can also just send the data to the object call without calling the function. This is just a functionality of Torch. It's the same thing internally. When I inherit from this NN module, these functionalities are become ingrained in that model. So we don't have to do some of those base work. Now we declare an optimizer. So essentially how a network trains is that this input passes through these neurons. it forms this complex nonlinear function. This first layer adds one kind of function to it, say an f1 function. Then the output of this f1 function goes to another layer, and it goes through a composite f2 function. And then finally output of this is the y, and then the y that we predict here, and we have a correct y label because this is unsupervised learning or supervised learning, and we have a correct output label. We can actually measure the difference of this correct and the prediction, and this is our loss. And this loss is then back propagated to tune these weights. We do not tune the tensors of our input or of our output, those are fixed ground truth, but any of the function parameters, weights, biases, we can tune. So then this loss is a scalar value, and we take gradients of this loss with respect to these weights and back propagate the gradient so that we can update the weights. We're going to talk more about this today and the different components of that. So that is why we declare an optimizer. An optimizer is what does this operation in a algorithmic fashion. So each of these optimizers, there are Adam, SGD, R-Adam, there are different kinds of optimization algorithms that has a set pattern of doing this loss and update using a learning rate, is that per update how much of this gradient you incorporate into updating a weight. And then you do this loss. What was this loss calculation? So depending on your problem formulation, you will use different loss functions. If you had a problem that was continuous space, like you were trying to predict how much money or how many days or something like that, then it's a continuous space problem where you use something like a maximum or a squared mean error. And then if you have a binary problem, which is classification of 0 or 1, married or single, then you use some different function. We're going to talk more about that today as well. So that is how we formulate. We give the training process how to compute this loss, what is the best function you can use between your predicted output and the correct output that will give you a best measure of this loss. And then you will compute the gradients of your network with respect to this loss, and you will step through this optimizer process, and this optimizer step will update all its weights, and then you can iterate through another epoch. And then finally, once you're done with the training, you take argmax of your predictions, and then you see the accuracy of if you predicted it to be 3, if it was really 3 or not. That is the accuracy calculation. We kind of set up a basic formula for it. So today we are going to build more on this. So last week what we did was we just said that, okay, let's do this. This is kind of a set formula, but we didn't really think about why we were doing that. Now, this kind of a problem, when I said that this image was broken down into like a list, that each of these pixel rows were laid next to each other and form a big list, that is one type of representation of a problem. And it depends on the network, because we used a multi-layer perceptron which took the input like that. That's why we had to do this processing to our input. But what if we want to process the relative information within this image? So when you split this image each row at a time, you're losing information where what was this pixel relative to this pixel, how many times this yellow pixel was there next to each other, how did it fade into another black pixel. So these kinds of informations that's relative, that actually forms an image, is important for a lot of kinds of data. Conventionally, we used images. We use this kind of a processing on images, but more and more we're finding that relative information within a input data set or within an input sample is very important. And this kind of technique is now used for natural language, for stock markets, a lot of other things. So how do you preserve this internal information? One way would be to just feed all of this, the whole image, together into a network. Or you could also say, this is a lot of 28 by 28 pixels, way too many input for the network. Does it really need so much? There is this huge space which is black. There is this huge space which is black, with the really information that's important is in this part. So why not just take it out? So we could say, make a small bounding box here, and only take this 3 out. But how do we know from the beginning if the 3 is here, and the 3 is not something like this or something inverted? So we do not know what this bounding box should be. And there are other techniques that find these binding boxes and things like that, but in conventional sense, you do not know what the data looks like, and so you want actually to have an outer bound. What if your tree started here? So this corner information is also important. So you take a bounding box outside, and then you kind of try to take out the abstract out, where are these points in this image where there is most information change. And that is done through a filtering process. If anyone is from an engineering background, it's very similar to normal filters, in convolution filters, low pass, band pass filters. So what we're doing is we are trying to take one kind of signal out by merging two signals. If you take a filter and convolve on this image, what we're trying to do is find those cells where there is maximum change, or there is a shift. So we can then detect edges, and we can detect regions, and things like that. So we will see today how to set that up. Now we can also think about how representing this input output. One hot encoding is something like representing something in forms of ones and zeros. An embedding vector is like a more continuous space. Now say if this was 0 to 10, I could represent my output as a list of 0, 1, 2, 3. Or I can say my output is actually 0, 0, 1, 0, and this one is when it's 3, this is what the output looks like. And when it is 2, this is what the output looks like. So this is called one hot encoding. You need to represent your problem and your input output in different fashion to meet performance and to meet the design of your network architecture. Now, normalization is very important, and also the distribution of your data. So something, we're gonna look at an example now. So if your input data was, say, something was an image that was very bright, it was like taken from a high resolution camera in daylight, and something was taken in a dark room with your phone camera that without a flash. So those image qualities are very different. The data distribution of intensity of those pixels are very different in that data set. So if you put all of those things together in one big data set and try to learn a network, it's gonna fluctuate a lot, and it probably won't get the patterns out that it needs to actually detect tree in any situation. So for that, we need to normalize all the given input data set with respect to each other, so that they are on the same scale in terms of intensity and what this information is. Then we compression, quantization. These are all very signal processing engineering kind of ways of looking at it. If you have a limit on how much data you can process, then you have to compress your data. How much can you compress something? If you had a 64 floating point value here, will you get the similar accuracy if you did a byte or an int? So quantization and compression are also very important aspects when you're actually building models. Now, we're going to look at a bit of a convolution network and what convolution actually does. And so the format of these slides are, I'm gonna just explain the concept a bit, and then each of these are linked to different resources, Medium, and there are a couple of people who write blogs, and these documentations are very good sources of information. And there's a lot to cover, and we cannot really go into the depths of everything in 2 hours. But if you do the follow-up work and read some of these articles, then you should get a fair bit of understanding of how the internals of all of this works. I will try to explain an overview and get you started on this as much as I can. So, like I said, a convolution, here you can have this image and you can say, I'm gonna convolve this with one dimensional array. Say I wanted just to detect an edge. If on one side of this image there was a green and on the other side was a black, and if I move this on top of it, then there's going to be a change, a shift when that edge comes. We want to detect that edge when that shift actually happens. So this is one kind of convolution which will try to find this one particular feature. Then if we look at a 2D convolution, then we take, depending on the kind of filter you want or the kind of feature you want to extract, you can set up different kinds of filters. Like here, if you wanted to just keep the image the way it was, you would use a filter like this. But if you wanted to detect edges, you wanted to blacken out or leave out all the information, or mask all the information that is not at the edge or at the borders of things, then this is the kind of kernel that you can use. And this will, as it moving along a matrix, it will pick up these edges, and that's the feature that you're going to feed into your network. You can also sharpen images and blur things. So something like this is like an average of all the pixels at a time. And then Gaussian blur is like a not a even blur, but a distribution of the center point of my filter is maximum, but then it fades away to its background. Um, so how this happens is that if you have this kind of a matrix and this green box is your filter moving across your data, then from each of these multiplications you come up with like a dot product of these two arrays, and you save that dot product into another matrix. And this is you can look at it as a compression technique, you can look at it as a feature abstraction technique. This essentially creates a secondary form of your input, and that can be, if depending on what your objective of your network was, you can represent your input in different ways. If it would help, if you wanted to augment your data set, you can do many such things with convolution type filtering techniques. So like I said, padding is important, because if your information was at the edge and you did this convolution, you might miss out this data. So having an external box helps generally in capturing all of the input. And so we are now looking at the convolution neural network PyTorch notebook. So you can go through this notebook and do more all of these exercises, but what I've done here is to just explain how you would initialize something like this. So NN is your torch.nn, torch neural network submodule of your PyTorch, and then functional is some module of neural networks, which is for all the helper functions, you can say, for optimization. All these different algorithms are put into a separate place, and then NN is gives you access to the default models, classes, layers, things like that. So you can use the NN module and call cov1d, one dimensional. So that is what we looked at, one list array. And this is kind of a filtering, like a convolution process that's going to happen. And now your input channels is how many dimensions are there in your data. So something like this, this is three images, let's say, and then each of your images has then three feature sets, and then each of them is like um, a channel of information. So if this was a picture, this is all the red pixel values, this is a blue pixel values, and this is all the green pixel values. And then this one is one image, and then you have multiple images in one batch, and then you have multiple batches in your whole data set. That is how your data set is going to be laid out when you load it. So this number of channels when you initialize a conv layer is how many input dimensions are there. So if my input was RGB, so it had three features, then it would be three number of channels. But if I say one, then I'm maybe looking at only a grayscale image, which only has like a pixel intensity value and not an R or a G or a B. Um, so then output channels, usually in a network, you can determine based on the network that you're building how many you want. And this is something similar to what we did here, that your network outputs, the number of neurons that you want to set up is in your control. So that's part of your design process. You can do that. Um, and then, so if you should be running this with me. And so it creates this is a kernel size, so this is a 3 by 3, or this, because this is a 1D, this is just a list of 3 elements. um, and so this is one list that got created, and now this is my input, which is another list. And when I convolve it, it takes a dot product of these two input and the CNN1D convolutions. So just to look at the size, this was my input size, which was 10. And then this was, when I laid it out like this, it became this one list was its own feature and in one batch. And then I passed this input through this convolution layer, and the output now is a 118. So this is how the dot product works. It is taking the dot product in that region and then coming out with a value for it. So you are compressing the information or taking out a different representation of it. So similar to 2D, here you're defining one channel, and your kernel size is 3. So this is a 3 by 3 because now your stride is 2. And You're convolving it, and you're coming up with a representation that is a convolution of those two things. So this is what happens when you pass an input data through a convolution network. It abstracts out this information into something smaller. And it's also like a feature mapping technique. So now we're gonna look at some default models in PyTorch for this kind of a CNN task. This CIFAR10 is another popular data set like MNIST, and you can load it like this. We talked about some of these things before, but when you're loading it from a data loader using a predefined data set, you need to specify batch size, how many batches you want to split that. So if you were on a GPU, you would use a larger batch, depending on how many floating points were there in your input data. You want to balance out your batch sizes so that you can process it on your CPU or your GPU. So in when you're building production quality models, running out of size like memory is a big problem. So this is an important thing to know, or to, well, you can do this later also, but in this is a design thing as well, not just in your network, but how to split your input data into batches. Now you always want to shuffle your data. Later on there is an example where if you didn't shuffle it, you can see how the performance differs. But what happens here is that per batch in your whole epoch, you are updating these gradients. Now, if you didn't shuffle it, the possibility is how the data was initially saved. The first 10 were all ones, and the next 100 were all twos. And so when you're batching it, you're probably not going to learn anything. You're not going to learn a loss, or you're going to learn a very drastic loss. Like if the actual label was one, your predictions initially were random, and everything was a one, what is the feedback that you're giving to your network? It's not a proper feedback. So because you're initializing a model from randomness, you actually want the labels to be shuffled as well, so that it has a possibility of seeing everything and seeing what it is wrong and what is right from this like initial random thing, random initialization, so that it can then start to tune towards a direction which is correct. But if you don't shuffle it, it will not know which direction is correct. So this is very important. And the number of work is like if you're doing it on a CPU, you can do it faster by using more CPU processes or threads. So this is your data type. When you first load this data, and previously we had seen that the data was loaded as a torch tensor, but this time this data is a NumPy array. This is how this data set has been saved. And so now you want to actually, before you train it, you have to take it into a torch tensor. So this is the whole data set. You can also access this data set using the data property of this data loader, which is only going to return you the X and not the labels. And now you have to convert this into tensor. So now this becomes a tensor. And now this transform stuff. Here I mentioned that you need to transform your data, where we looked at zero padding, this outer box to an image, and this convolution filtering as one kind of transformation. But the other kind of transformation is the cleaning of your data itself. So if your image was something rotated, like if you are building a model that detects if a vehicle is a car or a train, you are most likely going to take an image, in production of a car or a train that's lying on the ground, that's on its four wheels, or it's on the track. So the orientation of the practical image that you're going to get and the images that you have, they might differ. You might want to take tilted images of cars and trains and put that in your data set in as part of your data augmentation, so that you know how much differently you can take an image when you're actually using this model. It does well, but then it's also, would it ever be flipped completely 180 degrees? Will it be pointing to the sky? Then maybe not. So these are kind of constraints and design aspects, that how much of data augmentation is good and how much is too much noise that you cannot really process and generalize well for. Because if in your image you had 50% trains that was looking in the correct orientation and 50% pointing towards the sky, then you are going to need either a huge amount of data for it to generalize well, or you're going to get a very bad performance, or not as good a performance as it could have given if it wasn't oriented like that. So then it is up to the data scientists and people who build these models to condition the input data, transform it in ways from which a model can learn. So this transform is a good module given by Torch. It puts a lot of these functionalities, and if people are from MATLAB, that kind of background, this should be very familiar. You can transform any 2D array, 3D array with different operations like transpose and different kinds of things. So then transform, to find information on any module, you can do this on a notebook. Just put a question mark and you get the documentation. So it shows the different kinds of examples of transforms. You can have center crop and things like that. And if your input data was in form of NumPy array, then instead of doing this from NumPy yourself, before processing it, you can also give inside this transform compose this transform to tensor parameter, so that it will do it after it's done with all these other operations. So now this is one image from this CIFAR dataset. This is what it looks like. It has 3 channels. This is the RGB values, and then there are multiple images, and that's a batch. And if I now plot this image, I'm doing PLT show, which will give you an image representation, like a picture representation of this matrix. Then this is kind of what I'm getting. This is like a flipped train. Then I can do a kind of a transformation on it, and then I orient it in a certain direction, and it's now horizontal. But I can also do a normalize function. So this data was a kind of had its own distribution, but I can change the distribution based on different conditions. So usually what people do is this by 2 is like the variance parameter, and this 0 2 is a mean. So you kind of take your data point to like scale it down to the mean of the whole data set. So those are kind of normalization techniques. And depending on if your data was pre-processed or not, it might have these things inbuilt. So you have to kind of tweak it and see what kind of representation you get. You have to plot these distributions and see if it is normalized or not, if you don't know from the beginning. So now you can see that doing these transformations actually changes the quality and the representation of these images. So now another way of doing this transform, like I did the transform here manually to this image. But you can also, when you were loading the data, there is a way to mention that as a parameter. And so you define this, what kind of a transform operation it will be, and then send that into this data set module, and it will do all this operation on your data set while it is loading it. So this is how this data looks like. So does anyone have any questions at this point? Is everyone able to hear me correctly? Okay, I'm gonna take that as a no. Um, so essentially, just to repeat myself and kind of slowing it down a bit, what we did was we declared a transform, and transform is a class or a kind of a function within Thought Vision. And when I uh, call this transform, I call a compose function on this, and I give it all the different operations it can have internally. And then I send this operation in the loading time and say that while you're loading it, pre-process it. And now in reality, you would actually write this, load this data first, like here without a transform. You will first figure out what kind of transform it needs, look at the distributions and things like that, which we'll do in part 2, where we formulate our own problems and solutions. But for now, you would first figure out what the transforms needed, and then you would then later on, when you're training on different models and different techniques, once you've figured that transform out, you're going to save that and use that every time. And IM show is how you plot it on different images to see if your desired transformations are correct. Now, this is a convolution neural network. There are many different ways of declaring networks. We touched upon this last week. Um, this is this is a convolution neural network where I have declared, I've imported or taken inheritance of this base neural network. I have declared a convolution layer, which was we talked about in the beginning of this notebook. What a convolution will do to your input. We are just now putting all of these operations together. I am saying that I want a convolution network, and let's look at what a convolution network has. Your first input dimension is input channels. The second one is your output channels, and this is your kernel size, and stride by default is 1. So now you have 3 input channel, 6 output channel, and 5 kernel size, and by default stride is 1. This is your first convolution operation, and then your max pooling. What max pooling does is that if you have something like that box, something like this box going over this data, then you're going to take the highest value from this operation. So if your box was going for, this was a 2 by 2 box and it was moving across this image, this is a 1156, this was what your input data looked like. A max pooling would take the 6 because that's the max. This is very sudoku like matching kind of a thing, so it will pick the 6, and then it moves next. It will find 1 2 6 7, it will pick 7, it will pick 2 4 7 8, it will pick 8. So then it will compose these different representations of this. And that's max pooling. However, you can also say I want an average pooling, where you do 1 plus 1 plus 5 plus 6 by 4, and you can set up different feature extraction techniques like that. So usually max pooling is your most popular one, and so you do first do a convolution where you set up this filter process or a dot product process, and then you see what is my max pooling operation I want. So this is a 2 by 2, and then from this convolution, whatever output I got, I want to take the max box from this pool, and then you pass this into another layer, which is convolution neural network 2, and that has now whatever number of output channels this had, this must have the same number of input channels. And now I'm saying my output channels from here will be 16, and same number of kernel size. Now let's look at our problem. We want a network that is doing this convolution operation, but coming up with a final representation. So in my final output layer, my images, whatever they might have been, there are 10 classes. So there is a plane, a car, a bird. So there are 10 different classes, and my final output layer has to be a representation of these 10 things. So this is a linear layer. My final output isn't an image. There are some networks where it can be, where my network generates one kind of image given a kind of image. You might have read about things like that generates replicas of Picasso's work and things like that. So there could be networks where you compose a different representation of your input, in which case that can also be a different kind of an array, in which it can be a different kind of like a final layer. But here we are trying to predict a one out of these 10 classes. So this is a linear layer, and if it's a linear layer, then we want it to have like a softmax or like a probabilistic output from this. So we need to set that up. Now if my final layer is going to be linear and my input layer were these 2 by 28 by 28 image inputs, and that I have then taken a smaller representation of something like a 4 by 4 matrix, and I did this twice, then I need to take these boxes or this convoluted representation into this linear network. So for this, you usually put another linear network before it. So you not only learn the convolution layers, but you learn another linear layer that translates to this final layer. So we in this model have used 3 linear layers like that, and your final layer output will be the number of classes you have, which is in this case 10. And we're gonna try and tweak these parameters and see how it will affect the performance of the model. And so, as discussed last week, what happens in the forward function is that input, it can be a single image or a batch, it will pass through these different layers. So if I've declared this pooling layer, it will first pass this data from this convolution layer, then it will do an activation on it, which will be a ReLU activation, and then it will pass it through a pooling layer. So this pooling and convolution, these two things together forms the first operation of the network. Then the output of that network goes into another convolution where it does a conv2 and a pool from there. Now you need to transform the output of this to something that can go into a linear network. So you need to unfold this. This is again what we did previous week, where we took one image and we took the rows next to each other and formed it a list. So this is an unfolding operation. If you know my output layer, so this is something like a backtracking as well. Like if I know my final is 10, I wanted that final layer to have 84 neurons. So 84 came from 120, and 120 came from something substantially larger. So we can design this architecture like that. And so if I know now that my input to my linear network has to be this, then I'm going to automatically figure out what should be the other dimension, given whatever was the output of this convolution. Before you had to do this math yourself, but Torch gives you this view function where -1 will automatically interpret for you, given that this is what my input dimension to the linear network should be, how to unfold it and structure that data. So now this is the network, and we give it a cross entropy loss. Entropy is, in a very basic understanding, how much information you can gain by, or the uncertainty that is there. So if my data set was like all ones or all zeros or all cars or all buses, and my predictions were all zeros and all buses, there is much less information in that kind of a thing, because the probability of coming up with a bus is always a bus. And that is why also you need to shuffle it, because this loss then needs to have a good representation of all the outputs that it needs to see. So this cross entropy will be like, I had 10 possibilities, but this possibility was only this one, the other one was only that one. Or there's a soft value to it where something is 0.2 and 0.8, but it's learning the how informative this output is. And so from this information gain, we can compute a loss, that I got this wrong in terms of how much information I could have gained, and that is the loss that we calculate. Where something like, if my prediction was 100 and what the correct prediction should have been was 50.5, then I can just do a Euclidean distance or a difference or something like a error calculation that's mathematical, that is more intuitive, we understand. But here in this case, it is not a value or a set of values, it is different classes, where each class is kind of like, can be thought of like a binary of a being present or not. And then if you say or you figure out that this was present with certain likelihood, then how wrong you were or how right you could have been, that is the kind of measure that cross entropy will capture. So then that works out as a good criterion for loss. And you then for an optimizer, we are using SGD. We're going to look at what the different options were here, and then we pass the network's parameters, so all the weights and biases that's in the network. That is what this optimizer is going to update from this backpropagation operation, and then we have a learning rate and a momentum to it. So what we are saying is, per epoch of your data, and we are only going to process this data for 2 epochs, we have a running loss per epoch, and we're going to compute how much loss this was, and that is going to be a scalar value. And when we are computing this loss, we are not going to update the gradients. This is just going to be, no matter what it was, maybe at the beginning the network was completely random, all the weights were randomly initialized, but at this point we are not updating the weights at all. We're fixing the weights and saying, from this randomly initialized network, try to predict, given this input, what the output was. If the output was correct or how wrong it was, take that loss and then update the weights for the next iteration. So we freeze the output here, then we pass the inputs through our network, then we compute the loss. All of this done is keeping the model fixed. But when we do a loss backward and an optimizer step, that is when the weights got updated for the next iteration. And then we went into another for loop where, using these updated weights, it does another set of operations on the input. So we run this, and then we can do a prediction of how many went right and wrong. So you should be doing this with me. Is anyone having any issues? I might ask to ask people to share their screens next time. Right. So a convolution one versus a convolution two is a box or a list. That other filter can be either a box where it does pool information from that boxes next to each other. So if it was a 2 cross 2 or a 3 cross 3, it will look at 3 adjacent rows and 3 adjacent columns, and it will do that dot product in that box. Or if it were just a 1D convolution, then it can only go through one array at a time. So it will go through only one row. So if it was um, in this if it was a this is like a 2D thing where this green box is a 2D convolution, but if it were a list like this, like a 1D array, then at a time it can only go through one row, and then it will go through one row, move how many strides. So if it had two strides or one stride, it will move to this next place. Okay, so I missed a bit about the stride. So if my dimension of my kernel were 3, this is where I be, and then I have a stride of 1, so my next step I be here. And I can only go so much. That I cannot go another stride, because then you'll be out of this picture. So you can only do two steps in here where you take one stride. But if you had a two stride convolution network, you can only do one pass where you only do this much, and the next one then you can go to the next row and do this one. So that's why designing a proper convolution layer is important, because if your image was by 4 by 4 or 8 by 8, and if you did a two stride, then you're going to lose significant information at the end. So that's why
Yes,
it's
sorry. Are you trying to show us on screen? We can see it.
oh, okay, sorry. Yeah. So if this was the box, and my box was a 3 by 3, so my stride is, say, at this point 1, and I had this I had this box and my stride was 1. I had three boxes. So now this will overlay on top of this like that. And the next one, I can only move one step here. So next time it will be here. But then I can only take two strides, because the third stride I be out of this image. So for a 3 by 3 on a 5 by 5 image, I can only do two strides. And then the next one, I will go to the next row and repeat this process where I will here, because it's one stride and I have come here, and then I can only do another stride. Now if I had two strides, then I'd be first here, and the next stride I'm skipping these two, and then I would have to start here, but then I cannot finish it because there is nothing here left to go over. So I can only do one pass over this part with a 3 by 3 convolution layer if my stride was 2. So then, and if that is happening, then I'm losing information in these two boxes. And if this is just the image, then that's really bad, because then there could be a lot of information here. But that's why we use that outer bounding box. We pad that zero padding that image so that we can actually convert. We have to design that stride such that we can pass all of the input boxes in my input image at least once when I'm doing this convolution. And this is like a 2D operation, but if it were a 1D operation, then I would say only have this 101. And then I would go 101, 111. This is my dot product. So this is 1 times 1, 0 times 1, 1 times 1. So that is my output for my output of this layer. And then I move one stride, and then this is 110 and 101, again dot product, and that's what we get out. And then you move another stride, so we can only do one row at a time. Then we go to another row and repeat the process. So essentially, any kernel size, it determines how many dimensions you have in your network. Yeah. So all of these slides have follow-up tutorials and follow-up content. I for you guys to really learn and really need to practice. I can only give like a bit of a starter to all of this material, but to really start building things on it, and you will need to follow this whole series. You will need to get good with using the basics so that we can start solving some real problems, setting up some of this stuff for problems that has not been set by others. We have to come up with problems, come up with the data, and do stuff in part two. So yeah, this model is now trained. The You can see how the loss went down. So it was doing batches of 2000, and then the loss was at 2, and it went down to 1.24. And from last week, this is quite different. Last week we had this really rosy picture of a 97% accurate model, but something like that won't really happen. This is a much more complex data set and has more number of data points. So to actually get good performance from this data set was a whole competition, and lots of papers have been written about it. So if more people are interested, I have links to this. Two important things is we can do this accuracy. Sometimes it's good to not just look at the overall accuracy, but accuracy per class. So you may have a model that does very good on cats and dogs, but not so much on a ship. And depending on your application, that might be okay. Like you might expect cats and dogs to be a lot more frequent in the kind of data that you get when you really use it. One important thing is that you can save a model. So once you train this model, we didn't see this last week. Once you save a model, you can give it a path. And how you save a model is from this state dict function on it. This will actually take it will index, right? It will index that this neuron is the lth layer and it's the ith neuron in that lth layer, and then it will save the weight, the bias, everything that it learned through this training process, and it will save that in a dictionary kind of a format. And that's what the model really is. It is just a file where all these indexes are there and the different weights and biases and the gradients are saved. And that's the state of the model. Even the current gradient update, that state is also part of this state, model state that I'm going to save. And I can give it a path to save it at. And the next time, so I can stop a training process if something was a huge training load. I can do 10 iterations and save this model and upload it at a later point. I can upload it at a different machine. I can change the model slightly, a little bit, add a different final layer later on for a special kind of application, but still load the initial part of the model. And if it doesn't find indexes for another L plus 1th model or L plus xth model, then it will randomly initialize when I load this pre-trained model. So we'll look into pre-training and stuff later. Um, so this is and now there are many ways of calling or setting up these functions. This is a very good example of something more like a production quality, a more refined way of writing Torch code. I've linked this to the Medium tutorial. He has a lot more explanation. We're gonna run through this, but before we get into that, I want to talk about some of the concepts a little bit. Um, and we have about 40 minutes. Okay, so so we did a convolution network. We figured that what is a convolution operation on an input. We said we are going to take a feature out of this convolution. We're going to say max pool. So I'm say interested in the representation I get from a max pooling. And I can do this in many ways. I can say I want to take out edges, I want to take out gradients of blurring things. Depending on my objective, I can set up different kinds of convolutions, set up different filters, average pooling, and things like that. And that is internally to a model transformations, and then there are external transformations that you need to do to a data set to make it proper for your application. The next one is the activation functions, which is very important. We talked about this a bit last week, but it's important to understand this more in depth. And this actually comes from loss and backpropagation. And so it's important to understand them from a loss perspective. Activation, I can also say that, okay, I need a function. I need from an intermediate representation f naught, I need a function of an input and of a weights to represent this. So to get this function out, I'm going to call it an activation function. But then why not any function? Why not a parabolic function? Why not something very complex that itself has its own training parameters? Why to just stop at a ReLU or a simple thing? And that comes back to this loss calculation and how that is calculated. For this takes a while to understand. I have linked a bunch of articles and videos that explains it really well. And I would highly recommend seeing that to really understand what's going on. But just to give you an overview, is I'm saying that from my final layer, I had a predicted y and a true y, and I'm going to take some loss measure depending on my problem, and I'm going to calculate a loss, a difference between my prediction and the true one. Now, this loss is all that I have. What do I really have at this point? I have the after one epoch of training or one parse of the network, I have the true labels, I have the inputs, and I have the predictions. I don't actually have any control over the weights and the biases. So the only thing I can do is backtrack from this state. I can compute the loss. And so now, how did this loss come? This loss is at this final layer, one neuron predicts something, another neuron predicts something. Why does it? It predicted because it got a function that was dependent on the inputs here. So if my y naught at my layer 2, if I had a y naught representation coming out, then this there was a w weight associated to 2 to 3. And so I said, if this was my ith network, ith neuron, so I say in layer 2, my ith neuron has a weight connecting to my jth neuron in my layer 3, and then this has its own output. And the weight is now, this arrow is actually representing the weight and the intensity of this connection. It doesn't represent the output. This neuron itself has a value. That value is the output of this neuron. So this box or this circle, you can think of having its own value to it. And so this circle value gets a product of this row or this arrow value and comes here. And this happens for every circle in the previous layer. So now every circle in the current layer is dependent on the weighted product of all the values that it stored in the previous one. And then so did this one. Now to actually, but here this value itself of this circle is also not in my control. I can, this is fixed. I cannot even gradient update this weight. That makes no sense. What I can do is then I can take a gradient update of these weights. But how can I do that? If this is a function of these weights and the value here, and similarly how this is a function of this weight and this value is also a function of this weight and this value, and then this value comes from my input. So then this becomes a cross or a composite function of this activation function times this weight, this activation function, this weight. um, and that is what the only controllable parameter I can get. So when I get this loss, which is a scalar value, I can take a gradient or a difference of what I could have changed in this weight or in this activation function that would have made a difference to this loss. So that then you take a partial differentiation of each of these of the loss with respect to each of these weights and each of these activations, and then it becomes a kind of a uh, uh, dependent product of the differentiations of this, and across then this one comes from this, so it also joins to this one. So from this loss you can step by step compute backwards of what these differences should be, and it's arbitrary. If you think, then oh my god, how am I going to find out which weight needed to be updated, how much, to get this loss correctly? Exactly, you can't. That is why you need a separate optimization algorithm and lots of data, lots of epochs to do this process over and over and over again till it learns, sees these patterns, and doesn't need to update anymore. It's a very much a trial and error process. It will keep doing this till the loss tends to go down. And what we want to do as like the designer of the network or somebody whoever built this network or thought of this the first time, their objective was, the only thing that I can do here is once it starts to go down, once I find this path or this kind of a gradient rule update where this loss has started to go down, I want to keep pursuing that path. I want to keep doing what I did well before. So that is the whole training philosophy or methodology that the different algorithms try to capture. Is that once I have figured out, okay, this is a good way of doing something, I need to get better at doing this, I'm gonna try and make continuous improvements in that direction, so that I can meet that objective. And this is a article that talks more about this paper. There's a link to two articles that then links to these papers on how these things were designed. You can read more about this, but the intuition here is first randomly initialize all these weights, compute a loss, and then take a step so that this loss can be minimized, which is a differentiation of a scalar with respect to different parameters, and this is a partial derivation and a product of the different functions. And then you just take a step, give it a learning rate that's, you can say, arbitrary in the beginning when the first design was made. I'm sure they tried a whole range of values for it, but now from previous experience of other people, we know what kind of learning rates are good to start with, what kind of algorithms work well for these kinds of things. But in the beginning, it was completely trial and error, where you just give it how much can you update this to go down on the loss, and keep doing it over and over again till it converts. So you can obviously see the challenges here. Before, you didn't have enough computation power and stuff like that. So doing this over many iterations and figuring out these algorithms and stuff like that which would work, or these hyperparameters which would work, was a very difficult task. So one way of simplifying this was to come up with functions for activations that had very simple derivatives. If this function here, so I'm saying whatever came to this circle, this is this operation or this value. So if it came up with 4, that was a scalar value 4, that is a function of weights and the values of the previous layer. So how did it come up with 4? Is was through that function. And so you need to differentiate that function itself. When you are doing this backpropagation calculation, it will come in that equation. And the one good way is to come up with function activation functions that have very easy derivatives. And we do all of this, like most engineers do this in their first and second year courses. We learn of these trigonometric functions and things like that, that have easy derivatives, and it's very predictable and things like that. So something like uh, a linear function has a scalar quantity as its derivative. Something like this has a linear as its derivative in different regions. Something like this translates to another function, which is a known function that has its own calculation. And I think sigmoid and ReLU are two of the most popular ones that gets used as activation functions, is because that they are not only predictable, but they themselves are also functions of certain kinds, and that gives it enough control complexity, but yet it's easy to calculate these things. That's why that activation function works that way. Some people say that our brain neurons also work on some similar functions like this, but there's a lot of research going on to prove that. It's very difficult to know if really our brain neuron gets activated by a sigmoid signal, or it's a much more complex process than that. But it's a good enough approximation, and it has worked well. It's working well right now for the kind of tasks that we do. Um, Now, the second part of this is this loss, right? That, okay, fine, we compute some loss, we take a back step, we calculate these gradients, and we calculate the function differentiations, and then we figure out how to update these weights for the next iteration till we find this good path, and then we try to keep going in that direction. And this is also a representation of what I'm talking about. Some in the beginning you are here, you could go up, or in a bad direction, or you could go flip around, depending on what you started out with. But that's not what we want. Our ideal thing is something like this, where we do not wait, we are not so cautious in the beginning that we only take small steps so that it takes a long time to train. But we find a good direction, we take good, like make good progress in the beginning, where we know that there is still a lot ways to go before we find an optimal solution. We take bigger steps here, but then as we feel that okay, our loss update is not happening that much as it was before, right? So if before I knew my previous was 10, now I'm at 8, now I'm at 7, now I'm at 4, so I'm making this huge progress, from my past to my future. So I know I am going in a certain direction. I want to capture this information somehow, and I want to use that information. So that is something like a learning rate, and the optimizers, the different optimization algorithms try to use this information in different ways. I can go a little bit over this. So something like, we were first, there are different techniques of doing it. We can take even number of steps, or we can modulate our steps, but modulate in a way that we are still decreasing towards that direction. And so there are different ways of setting it up. The different optimization algorithms will capture. Yeah, so we have different kinds of optimization algorithms like momentum, and we use Adam and SGD mostly. But what these you can do a simple gradient descent, right, where there is no way of learning from my trajectory. I only take random steps. Like I do some action, I figure out a direction, I just go in that direction. I just reduce the weight in the direction the gradient pointed. And that is a basic way of doing it. But then momentum says, or like the different momentum based techniques say that I am going to add a velocity based on my uh, trajectory. If I was moving very fast in the beginning, I'm going to use this fastness information as well as the direction information to progress. And as and when I am slowing down, if I'm going from now 4.1 to 4.3, 4.31, 32, and if I'm slowing down in how much I'm gaining in my loss, then I'm going to change the step size so that I can actually stop and converge at a good optimum. If I don't stop or slow down, I can miss that point and oscillate to a bad point, and then to come back from a bad point to the right direction becomes very difficult. Once you lose this sense of direction, that this trajectory was leading me to a minimum, and if I have overshot that and I'm here now, to come back to that point will be a very big issue for the training. It will take a lot more iterations, computation power, all of those practical constraints. So we want to come up with the best optimization algorithms possible that will help converge fastest, in a way that it's not too cautious and it's always the same step and same slow process, but it's more adaptive to how it was. So by luck, if you when you initialize the model with random weights, you had a very good network and your loss was very low, you do not want to change that. You do not want to go to a bad network and then figure out a good network. You want to just cash in on that luck and try to find the best optimum solution. So if your biggest first step was it was a very big improvement, then you want to right away slow down and converge here, right? So how much slowing down or how much step, that itself then is a function of itself. So the different algorithms have come up with different techniques of doing that. um, Here for more details, and this will become more clear, and people who are not from a data science or a mathematic background, it might be a little difficult to get all of this at the beginning, but just understand that this is the basic intuition. And then RMS prop is and ADA delta were big steps where it's in the development of these techniques, where it said that this gradient update is going to be a function of my past and my present. So past is like I already know that I have decreased by so much, but future can also be calculated, where before I take a step I can do something like a look ahead and say, if I did this, how much I would gain out of that, and take that into account as well. um, and then Adam is something that mixes these two ideas of past and present and adaptation very well. And um, there are other techniques that does this. So one thing here, a little bit of a problem, is that what if I am missing out a good generalized solution? What if I'm just finding a very good minimum right at the start, which was very fitting to my training data only? And what if that minimum, though it was a minimum for my training data, was not the best solution that generalized for test data or for the real world data that I will be seeing? So that is also a concern, and there are many papers, many researchers who have taken different kinds of data sets and done more in-depth analysis of this. So if this kind of an approach of RMS prop saturates at this position, which is great for the training data but does not generalize well, then what generalizes well is the previous approach, where any direction, any step, complete random actions were good. So how do we combine these two things, where you do not only look at the past and the present, but you also encourage randomness, and and a more regularized approach of doing this is Adam. And later on our Adam, where you have combined these two concepts together and it has been found that sometimes SGD can generalize to unseen data better than Adam, but with our Adam it combines both of these two things well, and they come up with optimized solution for computation as well as for generalization. So that's kind of the basic intuition behind this. um, so now, well, we crossed so the loss function itself, we talked about. So we were here, we computed a loss, we found the gradients, we wanted to find the good function that will give us an easy gradient computation for an easy calculation. And we, over time, researchers came up with these good optimization algorithms, and these learning rates that help train models good for generalization and things like that. And now PyTorch and Keras and all these models have packaged these things up and have given you recipes to start you with. Because before, what we just did in a few lines of code and from using somebody else's notebook, doing this would have been a PhD work, right? So now all of this learnings from the past, we are gonna use and carry forward. And there is probably room for research or finding a better optimization algorithm or a better learning rate, but maybe not the thing to start off with when you're trying to just solve a problem or find an application for these techniques. Another important aspect is this loss function itself. This article is explains the different kind of loss functions and when to use what. And Medium, this machine learning mastery, these are some of the very popular blogs, and I find them personally very useful to learn different concepts. Because if you start off with a book and you don't have a lot of background, it might become it will take you a long time before you can start building things and make progress. So I usually start off with these tutorials. If I'm trying to learn something new, so I would recommend that you do the same. Um, and now this loss functions in this article explains very well when to use what kind of loss function. In general, if it's a regression problem where it is like continuous output, a 0, a 10, a 100, then you do a mean squared error loss, which is the same thing as a Euclidean distance or a geometric distance. It's very similar in concept. Binary classification, when you have to predict if something is true or false or a male or a female, there is only two options there, like a 0 or a 1, and then you have only one output. So then you use binary cross entropy, which is the same idea as how much information you gained from predicting something true or false or being correct or wrong. You do not go into the fuzzy details of it. And then for multi-class classifications, categorical cross entropy in general, and depending on how you formulated the problem and what was your softmax representation, you can tweak these loss functions and see which gives you better performance. Like we used a sparse categorical cross entropy before. That's because the way the data set was set up, it I they found that that loss works, gives the best results. I also tried many other kinds, and I saw that yeah, sparsity was the best. So whenever you are experimenting with a new data set, you have to try out all the different kinds of options. But then this is a good place to start with. Um, Now, before we go into Kira's and the other notebook, and we are closing in on time, talking about normalization in general. So, like I said before, if your image was something very in like different intensity levels, or you have all these like really sharp images from digital cameras and very blurry images from your phone or from a moving vehicle or something like that, and if you put everything together, then all of these data points have this uniqueness to it or this own bias to it, and you may not be aware of it when you're putting things together. Ideally you could take like a normalization of things that were from a moving camera, normalization from something that was more digital, and then put them together and then bring them down to the same scale. But many times you don't know, so you kind of normalize your data in the beginning, and that first notebook shows you there's a normalization process. But then even with that normalization of all of the data, so what a distribution or a normalization very rudimentary way is that if you have say a list of numbers, right, then from 1 to 1,000 numbers, and each number can occur any number of times, you don't know. When you put all these numbers together, you get a mean of this number, and then given any number, so if my mean was 5 between 1 to 10,000, what do I understand here? I understand instantly that possibly the number of numbers in this list that is close to this 1 to 10 range, or that is close to 5 to 6 range, is very high compared to the ones that is there in 9,000, 7,000, or 10,000. So we just by looking at the mean, I can picturize how the data is distributed in that list. There must be at least 800 fives or numbers around that for the mean to be 5. If the range is from 1 to 10,000. But then I can also say what so is the 10,000 range, if there are 5 data points, that's 9,000, the 8,000, are they not important? Well, that also depends on how many times those occurred. What if there was nothing in that list that was between 600 and to 9,000, and then there are a lot of numbers in the 10,000 range, and a lot of numbers in the one. So how that distribution really is, you need another parameter, which is like the standard deviation or the variance from this mean. So you can have something that is very, very different, and like how many of these numbers in that list are only one standard deviation away, and how many of them are like 10 standard deviations away. That is what gives that list a distribution. So same thing with your data set. How many of these pictures were taken from digital camera? How many were taken from a moving camera? How many of them were red in color? How many were then blue? How many were grayscale? All of these, how many of them, what is the mean of that feature itself, and how that feature is then distributed. If there are like outliers, if there are 4 or 5 things that's very out there, you might just want to omit them from your data set. If you know, if the distribution is more or less there for everything, that you can normalize everything and then say bring everything to the same mean. So if my red color mean for everything digital was zero point 0.8, and the red color mean for everything that was from a moving camera was zero point 0.7. I want to bring everything to a normal shared mean, and that is what normalization will do for you for your input. But even when you do that, and across when you're doing this loss calculation and back propagation, your layers, because your layers then also have an output. Your layers, if it is going to give a y naught output here, then this y naught is another kind of input to your next layer. It is the same thing as the data, but you don't have control over the output of this one, like you did for your actual input data. You cannot look at it, plot it at the beginning and feed it after normalizing it and after scaling it properly. So there needs to be, then people have found it from experimentation, that you need a way to normalize the outputs from these layers as well before they're fed to the next layer, so that these outputs are also on the same scale. If something is zero point 0.2 and something is 0.10, and you do not know, then these fluctuates a lot. So if you do a gradient propagation, there are things like exploding gradients and vanishing gradients. We can talk more in details about that next week. But if the value of something becomes very, very small and the value of something is very large, then there is a disbalance here. Some gradients will become huge and will then further lead to huge updates, and some things will not update at all and get stuck. So for to deal with those kinds of problems, and it's a very, if you understand why you're normalizing your input data, you will understand this as well. Then you can normalize or batch normalize the output of your layers, so that before they are fed into the next layer, they're on the same scale. So these are some of the basic building blocks or concepts, and if you understand these 4 slides, and go through these articles, then you would pretty much understand what you need to really start working on these kinds of models, and building your own things. There's a lot of research, there's a lot of in-depth stuff, but you don't need all of it to get started. So this is, let me hold off on this one. This article concentrates on more about how to build more professional structures. We're gonna finish off this today. Let's talk about Keras a little bit, and we are gonna continue with Keras next week as we go into TensorFlow, because Keras and TensorFlow share the API and share some of the concepts. So here, the same as before in NIST, the one we did last week, if we have this data, and now TensorFlow gives its own way of loading data, and NIST has its, Keras has its own data set module and MNIST, it's pretty much the same data, but the data is stored in a different way. So you do this, you plot your data, and this is when you're looking at it, this is the data you see. Now you will see here that the data is not scaled. It's something is 18, something is 253. The range of these values are like non-normalized. When you say non-normalized, you want something to be between 0 and 1 for all of these points in your matrix. And if you on the other hand saw this for the PyTorch one, by default when you loaded this data, it was already normalized for you. So this data you can see when I loaded it, it was already normalized between 0 and 1. Yes, Ted, maybe we can talk about this a little bit after. I need to finish this in the next 10 minutes. So now, now this one is not normalized. I now need to normalize my input. There are two ways of doing it. Either we can use TF Keras utils normalize module and normalize it like that. And now if I look at the data, it's now normalized between 0 and 1. There is another way of doing it. You can manually do it. So if I know that my largest number is 255, then I can just divide everything by 255 to get it to between 0 to 1. And normalize may or may not be doing the same thing internally. Normalize can also be dividing all the numbers by an L squared mean, or something like something that is a root over of all the values, or all the values difference from its own mean. So there are different ways of normalizing things. You can say, I'm going to first pick the mean of all of these numbers, then I'm going to take the difference of each number from this mean and then divide each number by that value. That also gives you the same thing, and different normalization techniques brings out different kinds of attributes in your data. Personally, I have found that L2 norm works very well for certain kinds of data sets, but you can also just scale it from with your largest number. Um, then for Keras, it is very similar to what we did before. We can build a model architecture, or we can also just call a model. And this is when here we build a network and call it a network and import from a neural network module, which is like a base class. We can do that in Keras as well, where we call a module, build a class, and then we inherit from this model class, which is its base class. It's the same thing as we did before, and in both Keras and PyTorch, we can do the exact same structure. Instead of calling it forward, Keras calls it call. So we can say this object dot call, or we can just pass the data into this object itself. It's the same thing as before, but Keras gives you another way of doing it, and this one I find is the more popular one, where this TF Keras models. This is the base class that we just inherited, but from the base class itself, we can instantiate an object using the sequential. So sequential is like a vanilla instance of the model, which will do something very similar to inheriting something. This is same as saying I'm gonna create an object of my base class, and then I have a way of adding functionality to my base class with using parameters. in very object oriented programming constructs, you can either expose these functionalities through a function or not. So Keras does that. You can then, after you've created an object of your base model, you can add the different layers to it, different pooling layers, different operations, and then train the model just as you did before. You can declare things internally after inheritance, create the model as a fixed architecture first and do it, or do it this way. So now model is a sequential base class of a model. This is the most frequently used one. There I have linked documentation for this in the slide and on this notebook that you should be looking at to understand this more. Now model.add keras.layers.flatten. Now this one is a linear network or a multi-layer perceptron network that we did last week. And this is not a convolution network. Here you're again taking these MList images, these 28 by 28 images, and unfolding that into one big list. And so when we did unsqueeze and process the data like that, we could also give a flatten layer to our network where it does this by itself, and then we only need to calculate how many inputs that the next neuron needs to take from that flattened list. And these are all design parameters. So then there is no need to do this design aspect where you did that. Okay, my dimensions of my image were 0 times 0 1, and then this was going to be my input dimension, and then my next layer of networks was number of neurons. Here you can just say this tfkeras.flatten and it will do this itself, and then this 128 is the number of neurons that is there in this layer, in the first hidden layer of your model. Now you're saying that activation use value, and same, you declaring another 128, and the final one has to be the number of classes, so which is 0 to 9, 10 classes, and then softmax, you're predicting a soft 0 to 1 value for each class. And then this is essentially your model. When you have declared it like this, you need something like a model.compile. And here and there are different ways of doing this. You can, in the compile statement itself, you can say optimize random. You give the loss as these string, they are kind of internally enums. It will convert which operation or function it needs to use from this string, and you can only use these predefined strings. And then there are metrics as well that no need to compute the accuracy yourself outside. It will do this when it is fitting the model. It will pop out this accuracy metrics and other metrics that's internally built. You could also have done this optimizer as a separate declaration as Adam, where you could have given learning rate as a separate input and then compiled it like that. So if I'm training this, we'll see the accuracy here. We'll also see how changing the from this is the default implementation, right? So if you don't have control when you did this, you don't have control, or you did not mention what your learning rate here should have been. So this is whatever the default implementation Keras gave you, you're using that one. And so you'll see how that changes when you specify the learning rate to be 0.01. And we'll also try another one where we do a higher learning rate, just to understand its effects. So training's done, accuracy is at 96. training it now by giving it my own learning rate. So then this one finished. This is 95 accuracy. So everything else was the same, but we are using a zero point zero 0.01 learning rate that I gave it, and we see there is about 2% decrease, or a 1.5% decrease in the performance. Now I'm trying a higher learning rate. So you can see the accuracy is really, really bad. Just by changing the learning rate, and the number of epochs also is a big factor. If I'm going to increase the learning rate so much, I need to give the epochs to be something like 100, um, and that's going to matter a lot. But keeping other parameters fixed, we are trying to see the effects. So now, this one, what I did was I introduced a batch normalization. This was, so let's see, previously I had a zero point zero 0.01 network, but the batch normalization was off, and that gave me 95. And now with batch normalization and the same 0.01, I get a 96, a slight change. Then I can also say, let what would happen if I use a smaller network. Okay, fine. This needs a reboot. So we are kind of close to the time. So these notebooks are uploaded in GitHub. You can try out all of these. So this has another example. You can try out more combinations like that, add more batch normalization layers, remove some of these layers, and see how the accuracy differs. Change the epochs and the learning rate. It's very good to experiment with these things. um, this is another way of declaring the same model, instead of saying model add, and then adding those separate layers. When I declare the sequential, I can also declare the layers as a set of parameters, as a list of parameters internally, and then I can do the same thing as training. And then there's the other way of declaring it through class declaration. So these are the main three conventions that you will find in different tutorials. And this is a very good example of something more robust. So the kind of experimentation I talked about here, where you change these different parameters, right? When you build a professional or a real kind of network, you want all of these networks to be tunable. You want to search for these optimum settings for that works for your problem and for your data set. So in that case, this PyTorch library has a lot of good object-oriented programming constructs that helps you build these kinds of setups more easily. This is one good example where you are declaring all these parameters as a searchable dictionaries tunes, and now I can give it more number of settings, how many I want, and then for each combination of a learning rate, a batch size of, when it's learning rate equals 1, batch size is 100, shuffle true or false, and then you can also add epochs to it, how many epochs you want to train. There are these different hyperparameters can be loaded in, and then you can set up a run manager to train this model with this current settings, save that model architecture, save the loss, accuracy, different metrics that you wanted to use, how long it took, and things like that, and save that into something like file, and go over, once you have generated a lot of experiments and stuff like that, you can go over the different settings that gave you the best results, and find patterns here of what kind of settings usually are giving you better things. And this is the more kind of a workflow that you will need to do if you were really trying to solve a new problem that didn't have a solution or a tutorial associated with it. Yeah, so run these notebooks, try to get this coding habits and stuff. We are going to, in part two, try and build things like this from either problems we find on Kaggle or that we kind of come up with ourselves. So we'll do this ourselves, and we want everybody to do this together at some point. I think we are close to time. Did anybody have any questions? Yeah, so yes, Keras is part of TensorFlow now. Keras before used to be like a wrapper for different couple of different libraries, where the libraries themselves had their own way of initializing models and building graphs and stuff like that. But Keras was object-oriented way of then integrating it. But then TensorFlow has acquired it, and now it's part of TensorFlow. So TensorFlow, you can access internal TensorFlow models using a TensorFlow graph structure, which we'll do next week. But then you can use this object-oriented programming construct using Keras. If classes are not uniformly distributed, then we try to either get more data, or we try to do data augmentation. We want uniformly distributed data, and we talked about this last week. Um, that is very important. If you have zeros, that is 0.1%, and you have 9, which is 10, 80%, then you're likely your model will always come up with that other 80% option, just because it knows that I have seen this 80% of the times. My best probability or best chance of getting things right is just to predict the most likely outcome of this whole setup. That is a very big problem, and so to get training data as balanced as possible is a very important thing. Usually, depending on the kind of problem, you can use data augmentation techniques, where given a certain class, you can take the input features and slightly change input features to generate more labels of things that do not have enough representation. Usually, you can also do augmentation for everything, and then subsample it down such that the labels are more uniform. So there are different augmentation techniques that we're probably going to be talking more about in part 2. AI, yes. So weight normalization rather than batch normalization. Um, Ted, what exactly do you mean by this?
So there's a, I don't know if everybody else is getting an echo here, but I'm getting a serious one. There's a, like, weight normalization is a technique that came out, I think fairly recently. It's still not, last time I looked a few months ago, it wasn't incorporated in TensorFlow library, but I think PyTorch had it. Anyway, it normalizes, rather than normalizing the activation, it normalizes the weights at each layer. And when the paper first came out, they said they got better results. A couple people that I've talked to, as part of our old group, they tried it with little success. So I was just wondering if you, in the real world, have seen it and tried it.
Not for neural networks, but weight normalization is a technique from some of the unsupervised methods, like for clustering and stuff, or other kinds of unsupervised techniques. Weight normalization is something that is done quite often. I done, like, for my research, I found very various applications for it. And I can see why they would use that kind of a technique for a neural network, but no, for using it to train a model, I haven't used weight normalization. But the idea, like, for anybody who in general, is if you have this unbalanced input and there is nothing you can do about it, or from hierarchical clustering or internal structure generation, things are just that are the networks, that the representations that are clustering together, that comes up. And there are other people who would explain neural network as a kind of a clustering technique as well. When you if you visualize layers and the outputs of each neuron, you can see that the neurons themselves, the kind of representations it learns this abstract cluster of features that are similar from throughout the data. So one neuron would learn a cluster of lines or certain kinds of lines. One neuron will learn a certain kind of spheres. That's internal structures to the images or something like that. In different applications is different. But the embedding of the features in the layers is very much like a clustering process. So when you have this kind of a hierarchical clustering in unsupervised learning, you try, and there are these clusters that have this feature representation which is very weak. In this case, it's not a count that you're normalizing, it's the weakness of that signal. This signal is very important. Like for a sentence example, if my the and comma and my the and the name of a person or a capitalized word, this had a very important feature to understanding the language. But this signal weight was very weak in the models that it trained for various reasons. For either there is a lot of other signals that are more important, there is not enough representation of this, or there is confusion between what that signal really leads to. So there is that confusion there. So when you normalize these signal strengths in hierarchical clustering, that leads to better deterministic behavior from what you want out of that clustering process. In my research, in my master's research, I did that a lot, where I was normalizing the signal strengths for each hierarchical layer in the clustering process. That led to better final determination of what these clusters were actually in the real world. As opposed to if I didn't normalize the hierarchical structure, then there was a lot of mixing of the different interpretations of these clusters. So I would assume that it's a similar kind of a concept, but it'd be great to try that for a real application.
Yeah, it sounds like it's a similar, conceptually similar reasoning behind it and why it might work. But thanks for your input.
Thank you. So normalize input batch, normalize what's the final input for say linear regression number output. So it could be one neuron that predicts one value. It would depend on how you would set your model up. So we normalize the inputs. Well, I mean, you wouldn't necessarily normalize your output. If your output was a regression problem, you want the actual value to be predicted, unless you've like formulated the problem as a probability or a percentage problem, then there'd be no need to normalize it. But what I think you mean by normalization is also what this balancing is. When you are normalizing an input data set, you're balancing the different features and bringing it to the same scale. And the balancing of an output is the same as normal or similar to normalization concept, where you want the mean and variance of all the kinds of things that can be seen on the output are equally likely or as equally likely as possible. Okay, I think we're out of time. Thank you, everybody. I'll share the meeting and the conference, the slides and stuff in a mail today. Thank you.